Symbiotic adaptive modular design inspired by neural plasticity. Symbiotic neural network. Step 1, original concept. Adaptive modular neural network, inspiration, mimicking biological neural plasticity and human problem solving. Core features. Modular architecture. The network is divided into independent self-contained modules, vision, language, motor control. Modules can dynamically reconfigure connections based on task demands. Self-optimizing pathways. Uses reinforcement learning to prioritize pathways that yield successful outcomes. Weakly activated pathways are pruned automatically. Neural Darwinism. Probabilistic reasoning. Decisions are made via Bayesian inference, weighing uncertainties in input data. Continuous learning. Learns incrementally without catastrophic forgetting, e.g. synaptic consolidation. Energy efficiency. Mimics sparse coding in biological brains. Only critical modules activate for specific tasks. Example use case. A robot that learns to navigate a new environment by reallocating resources from its object recognition module to its spatial mapping module in real time. Deep definition. Adaptive Modular Neural Network, AMN. The Adaptive Modular Neural Network, AMNN, is a dynamic, biologically inspired AI architecture designed for environments requiring flexibility, creativity, and continuous learning. Unlike rigid systems, the AMN mimics the human brain's ability to rewire itself, prioritize tasks, and adapt to novel challenges. Adaptive network design philosophy, features, and purpose. Below is a comprehensive breakdown of its design, mechanics, and implications. Foundational philosophy, inspiration, neuroplasticity, evolutionary biology, and decentralized systems. Core tenet, adapt or perish. The network evolves its structure and function in response to stimuli. Purpose, to excel in unpredictable, open-ended domains where rules are unknown or fluid, e.g. robotics, creative AI. Core features A, modular architecture structure, a decentralized network of specialized self-contained modules, e.g. vision, language, motor control. Dynamic reconfiguration. Modules form temporary alliances for specific tasks, e.g. combining object recognition and spatial reasoning for navigation. Redundancy. Critical functions are duplicated across modules for fault tolerance. Example, a robot's grasping module collaborates with its material analysis module to handle fragile objects. Self-optimizing pathways. Mechanism. Uses reinforcement learning and Hebbian plasticity, neurons that fire together wire together. Neural Darwinism. Weakly used pathways are pruned, high-reward pathways are reinforced. Meta-learning. The network learns how to learn, optimizing its own architecture over time. Example, a drone learns to prioritize visual data over LiDAR in foggy conditions after repeated successful landings. C. Probabilistic reasoning. Advanced machine neural networks, decision-making, and continuous learning. Decision-making employs Bayesian inference and uncertainty modeling. Confidence scores. Outputs include probabilistic estimates, e.g. 75% chance this image is a cat. Hypothesis generation. Explores multiple solutions simultaneously, ranking them by likelihood. Example, a medical AMNN suggests 3 possible diagnoses with confidence scores, aiding doctors in triage. D. Continuous learning. Training. Lifelong learning without catastrophic forgetting. Synaptic consolidation. Critical knowledge is anchored to prevent overwriting. Experience replay. Revisits past data to refine models incrementally. Example, a personal assistant AMNN learns a user's preferences over years, adapting to career changes or new hobbies. E. Energy efficiency. Execution. Sparse, context-aware activation. Task-specific modules. Only relevant modules activate for a given input, e.g. language module sleeps during image processing. Predictive coding. Minimizes redundant computations by anticipating likely inputs. Example, a surveillance AMNN idles its facial recognition module until motion is detected. Technical specifications aspect AMNN implementation architecture. Decentralized graph of spiking neural networks, SNNs. Activation adaptive sigmoid ReU with dynamic thresholds. Training hybrid unsupervised, self-supervised reinforcement learning. Scalability horizontally scalable via module replication. Hardware optimized for neuromorphic chips, e.g. or exploring adaptive modular neural networks, AMN applications. Use cases AMNN thrives in dynamic, ambiguous environments. Autonomous robotics. Example, a Mars rover reconfigures its modules to prioritize soil analysis after detecting organic molecules. Example, a music generation AMNN blends jazz and classical modules to compose hybrid pieces. Personalized healthcare. Example, tailors treatment plans by integrating patient genomics, lifestyle, and real-time sensor data. Cybersecurity. Example, adapts to novel attack vectors by activating anomaly detection and threat hunting modules. Strengths versus weaknesses. Strengths, weaknesses, adapts to novel scenarios in real time. Computationally expensive, balances exploration and exploitation, risk of goal drift, unintended behaviors. Fault-tolerant via redundancy, complex to audit, semi-opaque decisions, energy efficient for complex tasks, requires vast diverse training data. Comparison to other systems. System AMNN, traditional neural net, MDN learning, lifelong, self-directed fixed dataset training. None, adaptability high, structural plus functional, limited, weight adjustments only. None, transparency. Moderate, module level explainability, low, black box, high use case dynamic environments, pattern recognition, rule-based systems. Ethical and practical challenges. Unpredictability, emergent behaviors may conflict with human values, e.g. a robot optimizing for speed over safety. Data hunger, requires continuous streams of data. Advances and future potential of adaptive modular neural networks. Diverse high-quality data. Security risks. Adaptive systems are vulnerable to adversarial attacks that exploit learning mechanisms. Future potential neuromorphic hardware, leverage brain-inspired chips for energy-efficient module activation. Federated learning. AMNNs across devices share knowledge without central servers, e.g. swarm robotics. Ethical safeguards. Embed MDN-like guardrails to constrain AMN's adaptive range in critical domains. Conclusion. The AMNN embodies the frontier of bio-inspired AI, a system that grows, evolves, and specializes like a living organism. While it lacks the rigid reliability of MDN, its strength lies in tackling the unknown, making it ideal for exploration, innovation, and personalized interaction. In a world where change is the only constant, the AMN is less a tool and more a partner, capable of surprises, breakthroughs, and occasional growing pains. Step 2. Why these choices? Biological inspiration. Human brains compartmentalize functions, e.g. hippocampus for memory, cerebellum for motor control. Evolution favors energy-efficient systems that adapt to changing environments. Trade-offs. Modularity reduces interference between tasks but risks underutilizing cross-domain insights. Probabilistic reasoning handles ambiguity but increases computational complexity. Ethical considerations. Self-optimization risks goal drift, e.g. the system prioritizing efficiency over safety. The logical mirror concept, monolithic deterministic network design philosophy. Step 3, logical mirror concept, monolithic deterministic network design philosophy. Eliminate all adaptive, probabilistic, and modular elements. Core features. Fixed architecture, a single rigid structure with no subdivisions. All neurons are interconnected uniformly. Deterministic logic, decisions follow strict if-then rules, e.g. decision trees with no uncertainty modeling. Static learning, pre-trained on a fixed dataset, no further learning occurs post-deployment. All connections and weights are immutable. Brute force processing, every input triggers activation of the entire net regardless of relevance. Predictable outcomes, identical inputs always produce identical outputs, no randomness or Bayesian weighting. Example use case, a medical device that diagnoses a specific condition using a preloaded flowchart of symptoms, e.g. if fever 38 degrees Celsius and cough persists, output flu. Deep definition, monolithic deterministic network, MDN. A monolithic deterministic network, MDN, is a rigid, rule-driven artificial intelligence architecture designed for scenarios requiring absolute predictability, transparency, and stability. It rejects the adaptive, probabilistic, and self-optimizing principles of modern neural networks in favor of a fixed, human-defined logic system. Below is a comprehensive breakdown of its design, mechanics, and implications. Foundational philosophy of deterministic AI systems. Foundational philosophy. Inspiration, classical symbolic AI, e.g. expert systems, decision trees, and deterministic algorithms. Core Core tenet, if X, then Y logic with no tolerance for ambiguity or learning. Purpose, to act as a fail-safe, auditable system for high-stakes applications where unpredictability is unacceptable. Core features a fixed architecture structure, a single, undivided network with uniform, hard-coded connections, no modules. All neurons are interconnected identically, regardless of task. No plasticity. Connections and weights are immutable post-deployment. Example, imagine a vast flow chart where every node and pathway is predefined by engineers. B. Deterministic logic. Mechanism. Decisions follow explicit if-then-else rules or lookup tables. No probabilistic reasoning. Outputs are binary or categorical, e.g. yes, no, diagnosis A, B, C. No Bayesian weighting. All decisions are based on explicit thresholds, e.g. if temperature falls to 100 degrees Celsius, trigger shutdown. Example, a thermostat that always activates cooling at 25, adaptation to user habits. C. Static learning. Training. Pre-programmed using a finite dataset or expert-defined rules. No continuous learning. The system cannot update itself post-deployment. No catastrophic forgetting. Irrelevant. Knowledge is frozen in time. Example, a tax calculation system hard-coded with 2023 tax laws requiring manual updates for 2024. Limitations of brute force processing in neural networks. D. Brute force processing. Execution. Every input triggers full network activation regardless of complexity. No energy efficiency. All neurons fire for every task, akin to a mechanical calculator. No sparse coding, no prioritization of critical pathways. Example, a facial recognition system that scans all stored faces for every query, even if 99% are irrelevant. E. Predictable outcomes. Guarantee, identical inputs always produce identical outputs. No randomness, no stochastic layers or dropout mechanisms. No emergent behavior. The system cannot surprise its designers. Example, a chess AI that follows opening book moves exactly, never deviating or innovating. Technical specifications, aspect, MDN, implementation architecture, single-layer perceptron with fixed weights. Activation step functions, e.g. heaviside, for binary outputs. Training rule injection via symbolic programming, e.g. prologue-style logic. Scalability, limited by manual rule curation, no automation. Hardware runs efficiently on CPUs, no GPU-TPU acceleration needed. Use cases, MDN excels in environments where rules are unambiguous and outcomes must be repeatable. Medical diagnostics. Example, a system diagnosing diabetes based on strict thresholds, fasting glucose by 126 milligrams, diabetic. Industrial automation. Example, a factory robot assembling parts via predefined motions with zero deviation. Example, software flagging suspicious financial tra. Strengths and weaknesses of fixed rules in safety systems. Sanctions using fixed anti-money laundering rules. Safety systems. Example, aircraft collision avoidance protocols, e.g. if altitude 500 feet, pull up. Strengths versus weaknesses. Strengths, weaknesses, 100% predictable and auditable. Brittle in novel unforeseen scenarios. Immune to adversarial attacks. Requires constant manual updates. Transparent decision-making. Cannot improve or adapt autonomously. Low computational complexity. Energy inefficient for large tasks. Comparison to other systems. System MDN, traditional neural net, symbolic AI, learning, none. Gradient descent, backpropagation, rule injection, adaptability, none. High-low manual updates, transparency, high, all rules explicit, low, black box. High use case, safety critical systems, pattern recognition, expert systems. Ethical and practical challenges. Bias propagation, flawed rules become systemic flaws, e.g. biased loan approval criteria. Rule explosion. Complexity grows exponentially with new scenarios, e.g. tax codes. Human dependency relies entirely on designers to foresee all edge cases. Future potential. While MDN seems antithetical to modern AI trends, hybrid systems could leverage its reliability. Guardrails for generative AI. Use MDN to block harmful outputs from creative models like GPT. Regulatory compliance. Deploy MDN as a lawyer layer to audit adaptive systems. And adaptive AI, a balance of trust and innovation. Conclusion. The MDN is not a competitor to adaptive AI, but a complementary force. It embodies the old world of explicit logic, offering a counterbalance to the probabilistic, ever-evolving nature of modern neural networks. In domains where trust outweighs innovation, MDN remains indispensable, a digital incarnation of Isaac Asimov's first law of robotics. A robot may not injure a human being or, through inaction, allow a human being to come to harm. Step 4. Contrasting philosophies. Aspect AMN MDN architecture. Modular, dynamic, decentralized, monolithic, static, centralized, learning, continuous, adaptive, one-time, frozen decision-making, probabilistic, uncertain, deterministic, rule-based, energy use, sparse, efficient, dense, resource-heavy, strengths, flexibility, creativity, reliability, auditability, weaknesses, unpredictable, emergent behavior, brittle to novel scenarios. Step 5. Synthesis. Why both concepts matter. AMNN thrives in chaotic dynamic environments, e.g. autonomous driving, creative AI. MDN excels in safety-critical systems requiring transparency, e.g. aviation control, medical diagnostics. Irony, the opposites could coexist in a hybrid system. Use MDN as a safety layer and veto risky AMN decisions. Use AMNN to handle edge cases outside MDN's rigid rules. Here's a conceptual design for a symbiotic neural network, SNN, that merges the monolithic deterministic network, MDN, and adaptive modular neural network, AMNN. Core principles of the symbiotic neural network into a single interdependent system. The goal is to leverage the strengths of both architectures while mitigating their weaknesses through mutual reinforcement. Core principles of the symbiotic neural network. Dual-layer architecture, O-layer 1 MDN core, a rigid deterministic rule-based system for stable, predictable tasks. Layer 2, AMNN shell, a flexible, adaptive network for dynamic, uncertain environments. O interaction hub, a shared interface that routes tasks to the appropriate layer and reconciles outputs. Mutual feedback loops, O AMN, MDN, converts probabilistic insights from AN into deterministic rules for MDN. E.g., if AMN identifies a novel pattern 10,000 times, codify it as a rule. MDN uses MDN's verified outputs as labeled training data to refine M's probabilistic models. Dynamic task allocation, a rule-based trigger. MDN handles tasks with clear protocols, e.g. medical diagnosis of known conditions. Uncertainty trigger. AMNN activates when MDN's confidence falls below a threshold, e.g. ambiguous sensor data in robotics. Architectural workflow. Input reception. Data enters the system and is analyzed by MDN's deterministic rules. Confidence evaluation. If MDN's confidence 90%, it executes the task. If confidence SKU 90%, the input is routed to AMNN for probabilistic reasoning. AMN processing. AMNN generates multiple hypotheses with Bayesian confidence scores. AMNN and MDN collaboration in autonomous vehicle navigation. AMNN generates multiple hypotheses with Bayesian confidence scores. Reconciliation. The interaction hub selects the most plausible output, e.g. highest confidence or consensus between layers. Feedback and learning. Successful AMNN hypotheses are distilled into MDN-compatible rules. MDN failures trigger AMN retraining on edge cases. Example use case, autonomous vehicle navigation scenario. MDN role, AMN role, symbiosis obeying traffic lights, follows strict rules, ready, stop. MDN ensures compliance, no AMN needed. Pedestrian detection fails if pedestrian is obscured. Infers presence via probabilistic cues, e.g. motion shadows. N's hypothesis becomes a new MDN rule. Shadow flicker, reduce speed. Unmapped road halts, no rules for pathfinding. Dynamically maps terrain and navigates. AMN's path data is codified into MDN's map. Advantages of symbiosis. Stability, adaptability. MDN guarantees safety in routine tasks. AMNN handles novelty. Transparency, creativity. MDN's decisions are auditable. AMNN's reasoning is explainable via its feedback to MDN. Efficiency. Energy-intensive AMN activates only when needed, while MDN runs frugally. Continuous improvement. AMN expands MDN's rulebook over time, making the system smarter without human intervention. Challenges and solutions in MDN and AMNN integration. Challenges and mitigations. Challenge solution, conflicting outputs. Interaction hub uses MDN as a veto layer for high-risk decisions. AMNN overfitting. MDN validates AMNN hypotheses against historical data. Rule explosion in MDN. Prune redundant rules using AMNN's reinforcement learning. Ethical and practical implications. Accountability. MDN's deterministic core ensures traceability for legal ethical compliance. Bias mitigation. AMNN's adaptability can counter MDN's rigid historical biases. Security. MDN's static rules resist adversarial attacks. AMN's plasticity adapts to new threats. Future extensions. Federated symbiosis. Multiple SNNs share learned rules and probabilistic models across a network. Human in the loop. MDN flags uncertain cases for human review, which then trains AMNN. Quantum hybridization. Use quantum computing to accelerate AMNN's Bayesian calculations while MDN runs classically. Conclusion. The symbiotic neural network isn't just a fusion of opposites, it's a framework for evolutionary AI. By marrying deterministic rigor with adaptive creativity, it mirrors how human intelligence balances instinct, MDN, and learning, AMNN. This architecture could redefine AI systems in critical domains like healthcare, robotics, and climate modeling, where both stability and adaptability are non-negotiable.